Okay, again, part 7, differential operator. Okay, lecture 8, the Laplacian of a vector. You see, the vector v will derive just using the Vm Am, which they belongs to the space vector. Okay, Vm is the contravariant component of this vector v. Am are the bases. Okay, m is equal 1, 2, 3, because we are in this extrinsic geometry 3D. Now, again, in the non-conservative form, okay, we apply the nabla operator in the non-conservative form. You see, again, the nabla of vector v is just the divergence of this nabla v over here. Attention now, nabla v over here is a second order tensor, okay? Nabla v is a gradient of the vector v. You just do you see, this is the nabla operator, and this is the nabla operator applied to the vector v, okay? I use an arrow here. Let's put an arrow over here. See? Now, then I substitute the vector v, this is a vector v, as Vm Am. I just plug here. Now you see that I will, in this case, I will have, I think there is a mistake over here. So this, okay, that's okay. This partial derivative will apply to these three, attention now, here there are three variables, Aj, partial Vm respect to Xj, and Am. So this I have a triple product, okay? So that just remake this, okay, and just use the product rule, okay, just using the Aj, and this will be a vector v. You just look at here, see, derivative of Aj respect to Xi. Now, in this case, I just repeat this over here. You see, I'll put a red just for you to see how easy it is, okay? This here, okay? Look. I take the derivative of this and repeat this, okay? This over here, okay? Plus, in this case, Aj, okay? Now I take the derivative of respect to Ci of partial respect to Xj of this vector, just over here. Look, the second derivative here, see? So, I'm expanding now the first derivative, okay? You see, that's the first derivative over here. So I'll put a color here just for you to understand clearly what we are doing. You see, that's the first derivative over here, okay? Expand the first derivative. You just this term over here, okay? Let's put this, sorry. This is the green one here. You see the green? I'll just expand this, okay? Now, I will apply the Leibniz rule, okay? The product rule, okay? I have two variables over here, so I expand this in two terms, just easy. Then I substitute now to get the Laplacian, this is a vector v, okay? This is a vector v. So it's just this relation here. So you just follow. It's quite easy. It's just a derivative from calculus, okay? The calculus course, okay, in engineering. Okay? So this I expand this term over here. just substitute this derivative over there. And then I'll expand now the second derivative, okay? I'll expand the second derivative here, okay? It's just this term here, see? Wow. See? This term over here, this is the second derivative, see? You just follow carefully, you see that's quite easy, okay, to develop this. Now I'll substitute this term, so I have this long terms over here, log number of terms, which is just a substitution, okay? Now attention now, you see, derivative, you see here, derivative of AM, see, this case, see, J is the Christoffel symbol, second kind. You see, attention now, M and J, they are lower indices, okay? Although this J here is not lower, but is a covariant, because I see this J here as a covariant, as I emphasized, okay, several times before. So this I can write the relation between this derivative and the Christoffel symbols. Now, you see, similarly for the second derivative of this, you see, you just, in this case, expand this, so you substitute, then you get this long equality, okay? All these terms. You just look carefully, just, you see, here it is substitution only, okay? It's derivative, okay? Partial derivative and substitution. So you take a paper and write down, will be quite easy. Also, you can analogous obtain the Laplacian of this covariant component, VM, okay? Just doing the same procedures that we did here. Okay? There's a lot of terms over here, okay? Because you have a derivative, okay? That's a long term. That's it. Okay? There is no problem. Then